morning students. In this series of videos we are going to discuss about combined problems. So these combined problems are useful for determination of an organic compound by using different spectral data. So in third semester we are discussed UV visible spectroscopy, IR spectroscopy, NMR spectroscopy and mass spectrometry. So in UV spectroscopy it gives the information about the chromophore present in the organic molecule. So the application of UV visible spectroscopy is presence of chromophoric group, and in IR spectroscopy it gives the information about the functional group present in the organic molecule. And in NMR we have four important applications. One is the number of signals in NMR spectrum gives the information about number of environments of protons, and the multiplicity, that means singlet, doublet, triplet or quadret, gives the information about number of neighboring protons for the particular environment. And the third important application is position of the signal. The position of the signal gives the information about the electron density around a particular nuclei. If the electron density is high around one hydrogen atom, then the hydrogen resonate at a very low frequency and appears a signal at near to TMS. If hydrogen surrounding electron density is very low, then the resonance frequency of that particular hydrogen will be very high. Then it appears a signal away from the TMS, that is in de-shielding region. That means if hydrogen having electron density around that nuclei, then it produces a signal at a shielding region. If the hydrogen having less electron density around that nuclei, then it produces a signal at a de-shielding region. So this is the important spectral information. So in this in third semester we are studied about all these things, the application of UV, IR, NMR and mass spectrometry. So mass spectrometry is very important spectral information, that means spectroscopic technique to determine the moieties present in the organic molecule. So based on the molecularity we can determine the molecular formula, and based on the molecular weight, whether it is even number or odd number. Based on that we have to assume whether it contains even number of nitrogens or odd number of hydrogens, and the further fragmentance, that means the molecular ions undergo further fragmentation produces further data ions, that means there is 43 or 55, 65, something like that. Then the fragment ions gives some information about our organic molecule, that means which moiety is present in our organic molecule. So these are the important applications about these spectroscopic techniques. Now, by using all these spectral data, that means UV, IR, NMR and mass spectrometric techniques, we can determine the structure of an organic compound. Let us see how can we determine a structure of an organic compound in a systematic way. Here, in this first video, we are going to discuss one problem based on molecular formula. That means here we have molecular formula and IR data along with NMR data. So first of all we have to determine the double bond equivalence present in the organic molecule. Based on molecular formula we have to determine the double bond equivalence. So this represents equivalence of double bonds. That means here the cyclic ring is also considered as a double bond equivalence. That means, for example, we have to calculate the double bond equivalence based on some particular molecular formula. For example, it produces double bond equivalence is equal to 1. That 1 represents maybe the compound is having one cyclic ring or one carbon-carbon double bond or one carbon-oxygen double bond. That means the molecule contains one carbon-carbon multiple bond, or it is having one cyclic system, whether it may be 3-member ring, 4-member ring, 5-member ring, whatever it may be. So the double bond equivalence means molecule having either double bond or cyclic ring. So now the double bond equivalence can be calculated on the basis of molecular formula and which element is present in that. For example, if the molecule having carbon hydrogen or carbon hydrogen and oxygen, then the double bond equivalence is equal to Cn plus 1 minus Hx by 2. That means the number of carbons present in our molecular formula and plus 1 minus number of hydrogens in molecular formula which is divided by 2. Then we can get some number that represents the double bond equivalence in organic molecule. For example, the molecule having carbon, nitrogen, oxygen and along with one nitrogen, then the double bond equivalence is equal to Cn plus 1 minus Hx minus Nx by 2. So here the number of hydrogens is subtracted from hydrogen atom, then we get double bond equivalence. For example, the molecular formula having carbon, nitrogen and halogen, then we have to add the halogens number to the number of hydrogen atoms, Cn plus 1 minus Hx plus Xx by 2. That means here the subscript X represents the number that is present in molecular formula. So, for example, if the molecule having carbon, hydrogen, oxygen, halogen and nitrogen atom, then the double bond equivalence is equal to Cn plus 1 minus Hx minus Nx plus Xx by 2. So, based on the double bond equivalence formula, you can determine the double bond equivalences present in our organic molecule. This is the information about the double bond equivalence based on the elements present on molecular formula. Here, in our molecular formula, we have only carbon, hydrogen and oxygen. So that is why we have to follow the first formula Cn plus 1 minus Hx by 2. So now I substitute the number of carbons. Here the number of carbons in the molecular formula is 9 carbons. So that Cn plus 1 means 10 minus number of hydrogens in our molecular formula is 11. So that here the molecular formula contains 1 nitrogen and oxygen. So that we have to take nitrogen atom. Hx minus Nx by 2, 11 minus 1 by 2. Because the molecular formula contains 1 nitrogen atom, then the double bond equivalence is equal to n minus 5 is equal to 5. Here the double bond equivalence 5. Here double bond equivalence is equal to 5. So in this 5 double bond equivalence, maybe the double bond equivalence 4 is for one aromatic ring and other one for remaining double bond or other double bond. So if any molecule produces double bond equivalence more than 5, we have to assume the molecule contains one aromatic ring, because that is aromatic benzene. Here the aromatic benzene contains 3 double bonds on one cyclic ring. Here the aromatic ring contains 3 double bonds along with one cyclic system. So that the double bond equivalence for this benzene ring is 4. So here the calculated double bond equivalence is equal to 5. So in this 5, the double bond equivalence is 4 for aromatic ring, and it contains an additional double bond, whether it may be carbon-carbon double bond or carbon-oxygen double bond or carbon-nitrogen double bond, whatever it may be, that is confirmed in the further spectral informations. So this is about the information of double bond equivalence. Now let us move into the IR data. So here the IR data is 1708 centimeter inverse. So 1708 centimeter inverse indicates C double bond reduction frequency in carbonyl compound. That means our organic molecule contains one C double bonded O group and 3453 centimeter inverse, 3300 centimeter inverse. These two vibrational stretching frequencies indicates NH stretching frequency in primary amine or in primary amide. 3543 centimeter inverse and 3300 centimeter inverse. Both the values represents NH stretching frequency in primary amide. That means nitrogen is attached to 2 hydrogen atoms. That means it exhibits a doublet because due to asymmetric stretching and symmetric stretching. The 3543 centimeter inverse for asymmetric stretching and 3300 centimeter inverse is for symmetric stretching. So based on that, our molecule contains one amino group or one amide group, that is primarily initiated, and the two values 1200 centimeter inverse and 1100 centimeter inverse. That means 1200 centimeter inverse, 1100 centimeter inverse. Both the values will be represented as CO stretching frequency or is 1200 centimeter inverse is also indicates CC stretching frequency. So CO stretching frequency or CC stretching frequency is 1200 centimeter inverse and 1640 centimeter inverse. So 1640 centimeter inverse represents a C double bond C stretching frequency in aromatic ring or in alkyl molecule. Next, 750 centimeter inverse and 690 centimeter inverse. This is the most important information value for aromatic meta disubstitution. CH deformations in aromatic meta disubstituted benzene and 1400 to 1600 centimeter inverse. So 1400 to 1600 centimeter inverse. This value indicates aromatic skeletal vibrations. This value indicates aromatic skeletal vibrations. That is 1400 centimeter inverse and 1600 centimeter inverse. So based on higher data, we concluded that our organic molecule contains one C double bonded O and one NH2 group along with one aromatic ring. So the presence of aromatic ring is assumed in the double bond equivalence calculation. Now it is confirmed in the higher data. And again, the same benzene information is given in the NMR. So finally, we can confirm that in NMR data, presence of benzene ring is confirmed in the NMR data. So what is the conclusion from here? So in our organic molecule, we have carbonyl functional group and NH2 group along with one aromatic benzene system. That benzene is disubstituted in nature, that is meta disubstituted in nature. So it is further confirmed by NMR data. Now let us move into the NMR data. So let us see here. The NMR data is 1.35 delta, 3 hydrogens triplet. 3 hydrogens triplet means CH3 is attached to CH2. So this means the 3 hydrogens exhibits a triplet. So when it is exhibits a triplet, it is adjacent to 2 hydrogen atoms. Then it is exhibits a triplet. That is why the CH3 is attached to CH2. Then the third chemical value, then the third signal is also represents the same moiety. Here it is exhibits 3 hydrogen triplet, then definitely the molecule having another signal at 2 hydrogens quadrant or 2 hydrogens multiplet. If you have to see the third chemical shift value, the third chemical shift value represents 2 hydrogens quadrant. 2 hydrogens quadrant. So that CH2, CH3 in this 2 hydrogens is adjacent to 3 hydrogen atoms. So that is why the CH2 group is exhibits a quadrant in proton number spectrum. So based on the first value and the third value, that is the first signal and third signal, we can conclude that our organic molecule contains CH2 and CH3 group. That means ethyl group must be present in our organic molecule. We have to see the second proton number data, 3.85 delta, 2 hydrogens, broad signal. This is a very important signal. So usually functional group containing hydrogens, that means the hydrogens which are attached or the hydrogens which are present in functional groups, that means alcoholic containing compounds, phenols or aldehydes. Usually these functional group hydrogen atoms exhibits a broad signals. So in the NMR data we already said that the 3543 cm and 3300 cm, both the values represents the presence of NH stretchings. So maybe the 3.85 delta 2 hydrogens broad singlet exhibits presence of NH2 group. That means the 2 hydrogen atoms are in nitrogen atoms. Now let us see the 4 values: 6.85 delta, 7.18 delta, 7.31 delta and 7.42 delta. These are all the values is corresponding for the presence of benzene ring. Here these all values 6.85 delta, 7.18 delta, 7.31 delta, 7.42 delta. These all 4 values is for benzene system, because benzene exhibits a chemical shift value at 6.5 delta to 8.0 delta. The chemical shift value of benzene ring is usually depends on the substitution which is present on aromatic benzene. Usually, if the benzene, that means unsubstituted benzene exhibits a singlet at 7.25 delta, that 7.25 delta will be increases or decreases, that value is depends on, that means the change in chemical value of aromatic protons is depends on the substitution which is present on aromatic benzene ring. For example, if the benzene ring is substituted by an aromatic electron releasing group, for example, these lone pair electrons are undergo conjugation with adjacent benzene ring, so that is why it gets a negative charge 2 ortho positions on one para-position. That means the electron density at ortho hydrogens and para hydrogens will be increases. That means the electron density at ortho and para positions will be increases. That represents the 2 protons or the 3 protons undergo or exhibits a signal at a shading region. For example, if it is attached to the electron withdrawing group, then it withdraws electrons from benzene system, then the same 2 ortho positions on one para position. That means the electrons withdraw from benzene ring, then the benzene ring, the electron density at 2 ortho positions on one para position will be decreases. Then it exhibits a signal at de-shielding region. That means high chemical shift value when compared to usual basic value 7.25. So here we have 4 different values. One is at 6.82, another one is 7.18, another one at 7.31, and the fourth signal is at 7.42. So due to maybe the substitutions present on benzene ring, the values are varying. That means here the benzene ring having 4 number of protons. That means benzene is disubstituted. This point is already explained in higher data based on the signal at 750 cm and 690 cm. So here we have a confirmed information about benzene ring for the substitution of, for the meta disubstitution or disubstitution is based on proton and number data, because in proton and number data the benzene ring exhibits only 4 signals. That means other 2 carbon atoms having another substitution that does not have hydrogen atoms. That represents that the positions, that means the hydrogen atoms are replaced by another groups. Now let us see. So the 4 values is for benzene system and it is disubstituted in nature. So here we have 3 disubstituted systems. One is ortho disubstitution, and another one is meta disubstitution, and the final one is para disubstitution. So here one hydrogen is multiplied, another hydrogen exhibits a triplet, and another hydrogen exhibits a triplet. So if we have 3 possibilities for these 4 environments. So let us see which substitution it is. So for example, if organic benzene ring is ortho disubstitution, the organic benzene ring ortho disubstitution. Here the disubstitution is 2 types. One is symmetrical disubstitution and another one is asymmetrical disubstitution. That means the 2 groups present on benzene ring is similar, then it is called symmetrical disubstitution or symmetrical groups. If the 2 groups present on benzene ring is different, then it is called asymmetric disubstitution. Here for example is the benzene ring having similar substitutions. Then benzene ring exhibits 2 proton number sequence. That means the hydrogen which is adjacent to this substitution and the hydrogen which is adjacent to this substitution are similar environment. That means these 2 hydrogens are in one environment and exhibits a 1 signal, and these 2 hydrogens are in another environment. That means if the benzene ring is orthosymmetrical disubstitution, then the benzene protons exhibits only 2 environments of signal. That means the 4 hydrogens are in 2 environments and exhibits only 2 signals in proton number data. But here in our problem we have 4 environments of hydrogens. So we said that definitely the benzene ring is definitely the benzene ring does not ortho symmetrical disubstitution. Maybe it is a ortho unsymmetrical disubstitution. That means here the X group is replaced by Y. That means these 2 groups are different. Then these 4 hydrogens are in different environments. Then the 4 hydrogens are exhibits 4 different number signals in proton number. So here we have one possibility, that is ortho unsymmetrical. And let us see meta disubstitution. Here in meta symmetrical disubstitution also we have only 3 environments of proton, because here this hydrogen is 1 environment and the proton which is adjacent to this substitution and the hydrogen which is adjacent to this substitution, these two hydrogens are 1 environment and again this hydrogen is 1 environment. That means here it is 1 environment, it is second environment and it is in third environment. So if the benzene ring is meta symmetrical disubstitution, then it produces only 3 proton NMR signals, but in NMR we have 4 NMR signals. So that is why we skip from symmetrical meta substitution to unsymmetrical meta disubstitution. So again, this unsymmetrical meta disubstitution is also exhibits 4 environments of proton. This hydrogen is 1 environment and it is in another environment, it is in another environment, and the remaining 4th hydrogen is also in another environment, because the conductivity of all the hydrogens is different, like ortho unsymmetrical substitution. So in meta unsymmetrical disubstitution and para unsymmetrical disubstitution, we have the benzene ring exhibits 4 different environments of proton. So let us discuss whether our compound is ortho unsymmetrical disubstitution or meta and unsymmetrical disubstitution. If the benzene ring is para symmetrical, if the benzene ring is para symmetrical disubstitution, then the 4 hydrogens are in 1 environment, then it exists only 1 proton. That means all the 4 hydrogens are in 1 environment, so that in proton NMR it exists only 1 signal. For example, if the benzene ring is unsymmetrical disubstitution, that means para unsymmetrical disubstitution, then these 2 hydrogens are in 1 environment and these 2 hydrogens are another environment, then para unsymmetrical disubstitution benzene ring exhibits only 2 proton NMR signals. But here in our other molecule we have 4 NMR signals. That is why we have to left with 2 substitutions, that is one ortho unsymmetrical disubstitution and meta unsymmetrical disubstitution. So it is confirmed based on multiplicities. So it is confirmed based on multiplicities. Let us discuss the multiplicities of these 4 hydrogens and these 4 hydrogens. Here this hydrogen is adjacent to 1 proton. Usually it exhibits 1 signal in first it exhibits one signal and it is split into doublet due to coupling with the adjacent ortho hydrogen. Again, this HCl proton having meta proton, and it is again interact with the spin of the HC proton and it is split into a double doublet. That means it exhibits a quartet. It exhibits a quartet. Again, the second proton, that means Hp proton is exhibits 1 signal, and this Hp proton is interacting with 2 ortho hydrogens and it is split into a triplet. And further it is having 1 meta hydrogen and it is coupling with or interact with this Hg proton, meta proton, and each signal is split into a doublet. So that means this Hp proton exhibits a multiplet. Again, the same conductivity is available for Hc. That means this Hc is lying between Hd and Hb, so that first it is split into a triplet and again it is coupling with Ha, so then it is converted into a multiplet. The Ha conductivity is similar to the, that means the Ha conductivity is similar to the Hd. That means Hd is now first interacted with Hc and again it produces a doublet. Then this doublet is interacted with Hp proton and it is converted into a quartet. That means the benzene ring is ortho unsymmetrical or ortho asymmetrical. The benzene exhibits a multiplicity as 1 hydrogen quartet, 1 hydrogen multiplet, another hydrogen multiplet, and the 4th hydrogen also exhibits a quartet. That means it exhibits a double quartet along with the double multiplet. But let us see the benzene ring is meta unsymmetrical disubstitution. Here this hydrogen atom is interacting with 2 meta hydrogens, that means Ha, Hb, Hc and Hg. Now Ha proton is interacting with 2 meta hydrogens Hb and Hd and it is exhibits a triplet. And again the same type of conductivity is for Hc. Again Hc is ortho to the 2 protons, so that it is also exhibits a triplet. Now Hb proton is ortho to the Hc proton, that means first it exhibits a singlet and it is interacting with the Hc proton and it is converted into a doublet. Now the doublet is interacted with two meta hydrogens. That means each signal is split into a double triplet. That means it is as a multiplet. Again, the same type of activity is available for HD. Then it is also exhibits a multiplet. That means HD is interacted. Now HD is again first interacted with HC proton, and it is exhibits a doublet. And then it is having two meta protons. One is HB, another one is HA, and the doublet is split into a 6 signals. That means a multiplet. So here, if the benzene ring is meta unsymmetrical lattice constitution, definitely we get two triplets and two multiplets. So based on all this information, we confirmed that definitely our benzene ring is meta disubstitution. This point is actually we discussed in a year. But based on 750 centimeter mass and 690 centimeter mass, but it is confirmed in NMR. So here we have meta disubstitution ring along with CH3, CH2 and 1NH2 group. So the moiety is present in our organic molecule is what are they? One meta disubstituted benzene ring and CH3 CH2 group, that means tail group, and one amino group. Let us see the molecular formula is equal to our moieties or not. Here in our molecular formula we have one hydrogen and it is observed in the amino group, and the molecular formula having 9 carbon atoms. Here we have only 8 carbons because the 6 carbons for benzene and 2 carbons for ethyl, and we left with 1 carbon atom. And here the number of hydrogens is 11. Definitely we can write the information based on NMR data, then definitely the 11 hydrogens must be equal. So that we left with 2 oxygen atoms. We left with 2 oxygen atoms. The first idea data 1708 centimeter mass indicate the presence of C-level bonded group. That means the molecule having one C-level bonded group. So that we left with 1 oxygen atom. Then we discuss this oxygen atom is attached to which moiety. This oxygen atom is attached to which moiety. Here, see this value 4.18 delta, 2 hydrogens quadrant. Here, the chemical shift value of the 2 hydrogens quadrant is very high. Usually, the alkanes exhibits a proton chemical shift value at 0.9 delta to 2.0 delta. Usually, if it is attached to one carbon atom, the carbon is attached to another carbon, then definitely it exhibits a chemical shift value nearly 1.5 or 1.3 delta. But here, the chemical shift value exceeds 4.0 delta. That means that particular carbon atom is definitely attached to one strongly electronegative atom. Here the strongly electronegative atom is oxygen. That means the CH2 group is definitely attached to the remaining oxygen. That means here you have to attach this oxygen to CH2 group. So here the oxygen is more strong electronegative atom. That means if you withdraw electrons from this carbon withdraws electrons from attached hydrogen atom, so that the electron density around that 2 hydrogen atoms will be decreases, then it is exhibit a signal at de-sheeting region or higher chemical value. So based on all this information, we get 4 moieties, that is one meta isotopy benzene ring and one ethoxy group, and it is attached to C-level bond and NH. So that's we have to write or we have to attach all these structures, all these moieties. Now I write C double bonded O, CH2, CH3, and we left with one amino group. We can also write on benzene ring, and it is attached to C double bonded O, and it is attached to NH2 and O, CH2, CH3, CH2, CH3. So this is the basic information based on the NMR data and IA data. We have 2 possibilities to our structure. So which one is correct? Let us discuss. Here we have to study the proton chemistry values of benzene ring. The proton chemistry values of benzene ring is 6.85 delta, 1 hydrogen doublet, multiplet, 7.8 delta, 7.3 delta, 7.4 delta. Here in IA data we have 1708 centimeter mass. So this value is very important. That 1708 centimeter mass indicates C double bond switch frequency in conjugated carbonyl. Compound. That means in aldehyde or ketone or ester. Usually here we have one ester functional group. That means it is conjugation with aromatic system. So then only it exhibits 1708 centimeters. But in this structure, our functional group is amide. Usually aromatic amide exhibits a chemical value at 1680 centimeters or 1685 centimeters. So based on that simple IR chemical value, you can confirm that the first structure is the correct value for our given data. So the second structure is not matches the NMR or NMR or IR data. So here the chemical values. So these 4 hydrogens exhibits these 4 informations. One is 6.85, another one is 7.9, another one is 7.31, final one is 7.42 delta. So this is the information based on given data. So based on NMR data and chemical values and IR data at 1708 centimeters, we can confirm that first structure is the exact structure for our organic molecule. So let us see second problem in this video.